So week 7, exercise 618. I apologize for the delay. You might already have solved this assignment without my help, but just in case you're stuck or you haven't started yet, here's something to get you going. So this week we consider problem 618, where we look at Poisson's equation that's written as nabla squared of u is equal to f of x comma y for x comma y in D, where D is the unit square which means it's the square in the plane that looks like this. So here we have the y-axis, here we have the x-axis, then this is what we call D. So what is this thing over here? This symbol is what we call the Laplacian. And in layman's terms, it means that we take the partial derivative of u twice with respect to x, and then add the partial derivative of u taken twice with respect to y. So this is what this operator means. This operator means the sum of the double partial derivatives. So actually we can also write Poisson's equation up like this. So Poisson's equation can be given by this equal to f of x comma y. So Poisson's equation is given by double partial derivative with respect to x plus double partial derivative with respect to y of u equal f of x comma y. Now note that this reminds you a lot of another equation that you've actually seen in the book. That equation is called the Laplace equation. Which is given by, well, the Laplacian of u equals 0. So this reminds a lot of this. So when we have to find a difference method to solve this, it's a good idea to look at the difference method that's used in the book to solve this. In 618a, we are asked to write down a finite difference approximation of this problem over here that has a truncation error of O of h squared plus O of k squared. Now, the method that's given in the book to solve this uses a difference approximation that has exactly that error, so it's a good idea to just follow the book's section 6.2 when we want to find a difference approximation for this and for this. Now, before we get started, let's just look a little bit more at what the exercise gives us of information. It tells us that we consider this problem on D, which is the unit square. And apart from that, it also tells us something about the boundary conditions. So what we are told about the boundary conditions is that u is 0 on the boundary of D for all x comma y on boundary of D. And note that this kind of boundary condition? Well, it's the first time we actually work with this kind of boundary condition, because earlier when we worked with partial differential equations, when we looked at the heat equation, you had a boundary condition here, here, and here. You didn't have anything up here. And when we looked at Black-Scholes, we had a boundary condition here and here, and then we had the terminal condition up here, but we didn't have anything over here. So now we actually have boundary conditions around the whole domain, which is, well, that's a first timer there. So that also means our matrix equations will be a bit special. It means our indexing will be a bit special. So we have to really consider our grid and write down which things that we know, which things we don't know, etc. So that's what we will be doing in the next video.